Hi guys, BuildZoid here, and today we're going to be taking a look at the RX 5700 ITX from Powercolor. So obviously this is a ITX ITX RX 5700. Now there's not really like an ITX GPU form factor as far as I know, but the basic idea of ITX optimized cards is they're smaller, right? So they're just within the ITX motherboard length. So the card's not going to be like longer than your ITX motherboard. And the end result is that there's not much space to actually fit anything on them. So you lose things like display outputs, and you only have one power connector instead of two. Which isn't really, like, I don't consider that a particularly big deal, but it's just like, yeah, you do lose the extra power connector that you would get on something like a full, on the full length cards. And the bigger deal, in my opinion, is actually losing the display output because, I don't know, like, you might want to hook up 4 monitors. Well, with this, you definitely can't. So yeah, you only get a DisplayPort HDMI and then another DisplayPort instead of the 2 DisplayPorts and 3 DisplayPorts and 1 HDMI on regular RX 5700, regular RX 5700s. There's obviously some exceptions that might have more display outputs than that. Anyway, with that out of the way, and there's like no dual BIOS or anything like that because there's obviously no space for overclocking features. So with that out of the way, let's talk about the power delivery. So this right here is the VCore VRM. So that's our VCore. It's a 7-phase, which is kind of the norm for RX 5700s and 5700 XTs, though it is worth noting that the RX 5700 reference card is a 6-phase, not a 7, because that was how AMD decided to like save costs on the 5700 reference card instead. And it's really weird because like I'm pretty sure that phase costs like $2 or something, and it's just like, yeah, remove the $2 worth of inductor and power stage. And when the rest of the PCB is just so horrible, like, well, not for this video. Anyway, so this is a 7-phase. It's controlled by this chip right over here, which that's a IR35217, running in 7+1 phase mode. That +1 is for the Soc Rail, which is down here, right? So that's our Soc VRM. Yeah, so the IR35217 is like the standard controller for AMD GPU, for modern AMD GPUs. Like, this is the standard controller. It's actually like the top. Well, the thing is, AMD hasn't really put out cards without a 35217 recently, which is kind of not a good thing because the 35217 is a pretty high-end voltage controller in terms of both phase count and feature set. And it's kind of expensive. And so the thing is like, even something like a 5500 XT actually still uses a 35217. And it's just like, AMD, that's probably not the best for like, cost optimizing a low-end card. But yeah, that's kind of what's going on with voltage controllers on AMD GPUs. And the main reason for this is basically the 35217 is the only controller that, like, I'm not sure, I'm not 100% certain about this, but my guess is that the 35217 is the only voltage controller currently available that supports the latest power management requirements that AMD has for their VRMs. So basically, you can't really use a cheaper controller because then all of the boost algorithm, voltage control, voltage adjustment stuff won't work properly. So you're stuck with this thing, which is very expensive, but that's fine because it's like, well, if you're an overclocker, that's great because you get a nice VRM controller with really high performance. If you're a GPU manufacturer trying to make, low-end GPUs, this sucks because you can't make, you need to spend money on a really rather overkill voltage controller in a lot of cases. Anyway, so yeah, that's kind of what's going on with the control scheme. And the 35217 is also made by Infineon/International Rectifier because Infineon owns International Rectifier. Anyway, let's talk about the power stages in our VCore VRM. So for the power stages, Powercolor has gone with TDA, that's not an A, 21232s. And these are 55 amp smart power stages. The MSI 5700 XT Gaming X also uses these. These are really good. These are really, really good power stages. So Smart power stages just generally are kind of more efficient than other types of power stages, but the main thing that makes them smart power stages is that they integrate a, well, more accurate than normal current monitoring system. So there are some other types of power stages that'll include current monitoring functionality. It's not as accurate. Well, it's not necessarily as accurate as what you'd get on a smart power stage. Basically, Intel rolled out a new spec for power stages where it was like you need a current monitoring system built into the power stage that is at least this accurate. And yeah, if you can't do that, it's not really like, if you can't quite meet the spec. Like, well, there's a bit of room, but like wiggle room with how accurate you can be, but basically you can't have it be horrifically wrong. And then still call yourself a smart power stage. They also integrate overcurrent protection, over temperature protection, which also means they have temperature monitoring built in. What else is there? Oh, and then like a bunch of other safety features that I don't care about, so we're not going to list them. Anyway, these are very, very efficient, and with a 7-phase of these, the VCore VRM on this thing is actually very capable. And I assume the reason why Powercolor opted for these, because the funny thing is, like, the other power stages that they're using on this card are actually even are weaker than what you would see on any other 57, well, weaker than anything I've seen on any other 5700 or 5700 XT. So it's kind of interesting that like the VCore VRM actually gets some really nice power stages, and then everything else is like even more of a downgrade. And I assume the reasoning for this is that the VCore VRM is just like that's where you need the efficiency, right? And this being an ITX card, you don't really have a lot of space to build big VRM heatsinks, and so I assume the Powercolor basically was like, well, we want the VCore VRM to run cool, and the easiest way to get your VRM to run cooler is to just not have it produce so much heat in the first place, where the, very nice 55 amp smart power stages come in. Now, the issue with these lovely power stages is that there's kind of two problems with them. There's no public data sheet, though I do have my own sources, so that's not really a problem for me. And said non-public data sheet is entirely spec'd in 1.8 volts because these are designed for Intel Xeon servers, not GPUs. Navi runs on less than 1.2 volts, so I had to scale down the efficiency curve of these based on like other similar components, which means not very accurate. But the problem is, like, if I did the efficiency at 1.8 volts, it would just look like basically this would look a lot less efficient than it should be. So yeah, I have tried to scale it down to 1.2 volts, but it's not like basically I'd say like plus minus 1 or 2 watts on every single heat output. Actually, that's kind of too much. It's maybe like plus minus 1 watt. Okay, like I did look through a lot of parts and tried to find something where it's like it's relatively safe. I didn't go with because the thing is, in my opinion, it's better to underestimate how efficient the VRM is rather than overestimate it. So I actually went with some of the parts that are more optimized towards high voltage than low voltage. So basically, there's some parts that have that are more efficient at 1.2 volt. Okay, no, but like you can get parts that at 1.2 volts, 10 amps, will produce, say, 1.2 watts of heat, and you can also get parts that will produce 1.3 watts of heat. So instead of going with parts that are 1.2 watts, I went with 1.3. There, that's what I was trying to get at. I was going with the parts, and they're 1.3 watts, but if you scaled both parts up to 1.8 volts, they might both produce 1.7 watts, right? Like that is actually possible. Like you can get power stages which will start 1.7 watts will go to 1.3, or a different power stage can actually go to 1.2, depending on just how the high side and low side MOSFETs are balanced in terms of their capabilities. So yeah, if you have if you have a worse high side MOSFET and a better low side MOSFET, you get better low voltage efficiency. And if you have a worse low side MOSFET and a better high side MOSFET, you get better high voltage efficiency. So Yeah, and I went basically with the, for a VRM like this, where you're outputting 1.2 volts, you'd actually want something with a really good low side and not necessarily such a great high side. And you don't really need such a great high side. It's not that you, like, if you have an amazing high side, it doesn't hurt anything. It's just, like, not necessarily that useful to have an amazing high side. So I basically went for this, for the scaling, I went with something that's more optimized towards high voltage than low voltage. So these aren't going to be, so it's more like I might be like 1 watt too high rather than 1 watt too low, right, on the heat outputs. Anyway, let's get into them. So 1.2 volts, 600 kilohertz switching frequency. This is just what the data sheet is spec'd at. 5 volts drive. I don't think the card actually runs that. It's probably at like 300 or 400 kilohertz. 5 volts drive voltage. The 5 volts rail is probably this right here. And these are power stages, so they just run off of 5 volts. There are some other power stages out there which you can run on like 6 volts and even 7 volts. And actually, you can overvolt anything if you feel like. You can overvolt anything you want as long as you don't expect it to continue operating reliably for the rated lifespan, right? Like, and depending on how much you overvolted, that's how much lifespan you're taking out. So yeah, but anyway, these run on 5 volts, and they'll run them on 5 volts because you don't really want to be overvolting your power stages. Though there are some GPUs out there in the past where you'd have like 3553s running on 6 volts, which is not which is not ideal for the lifespan of the power stage, though it does improve the efficiency. Anyway, let's talk about the heat output on this card specifically. So 150 amps output, this VRM will produce about 12 watts of heat, which is absolutely great efficiency for a VRM on a 5700 or a 5700 XT. Like, these power stages are pretty freaking great. And that's even considering that I went with the scaling factor where it's like suboptimal for 1.2 volts. If I went with the optimal one, we'd be looking at like 10 or 11 watts if I remember correctly. Because I initially scaled according to one part and I was like, this is too efficient. This looks way too good. And so then I started looking around for some other power stages to compare against, and I was like, okay, well, we'll take something that more like this. Anyway, 200 amps output. This VR should produce about 18 watts of heat. I'm not saying it's not impossible for these to produce less than 12. It's just like, I just to be safe, I went with the higher value. 250 amps output. This will produce about 25 watts of heat. And 300 amps of output. It'll produce about 34 watts of heat. And actually, like, the data sheet ends at 50 amps per, like, 50 amps. So, obviously, with a 7-phase, that tops out at 350. So, anyway, but 350, this would do 46 watts. So, that's why we stopped there. Anyway, practically speaking, you're not going to go past 250 amps. And, in fact, I'd be very impressed if you get 250 amps without, like, water cooling on the card and unsafe for long-term use voltages, let's say. Right? So... yeah, so within the like current draw range where you'd actually want to run the card, and also this is an ITX card, you're probably not going to be pulling off the heatsink, and the heatsink's not exactly huge, so I don't really see, like, this VRM is probably never going to have to see more than like 200 amps of current draw, just because there's not enough cooling for more than 200 amps of power, like for more than 200 amps going into the core. And so within that kind of load range, this VRM actually has absolutely great efficiency. Like, and in fact, it has great efficiency all the way up here, but it's just like in this range, like, it's not producing much heat whatsoever. And I think that's the main reason why Powercolor opted for these really high, like rather high-end power stages, is just like, well, it's an ITX card and there's not enough space for huge heat sinks, so make the VRM ridiculously efficient, and your smaller VRM heatsink doesn't have to work as hard. And so, yeah, the VRM here is actually pretty damn impressive. I wasn't expecting to see a bunch of 55 amp smart power stages on the card. Anyway, moving on to the SoC VRM, this uses just an NCP 302045, and this is just a 45 amp power stage. And the interesting thing about this is where the VCore VRM is actually better than a lot of other 5700s and 5700 XTs out there. This right here is actually just worse. I don't think I've seen a card with less than a 55 amp power stage on the SoC rail. Now, the SoC rail is a much lower current rail than the VCore rail. I don't think you would really ever want to overvolt it either. So I don't really see a problem with this, because this shouldn't really be dealing, like, you're not going to be massively increasing the amount of power draw that, you know, is being applied to that rail. So using a slightly weaker power stage isn't really a big deal, since the rail already doesn't produce that, like, output that much current to start with. But yeah, these are like, this is just a weaker power stage than what you would get on a lot of the other cards. And this one isn't smart. This is just a DR MOS component, so it's literally just a driver and two your high side MOSFET and your low side MOSFET. There's also a thermal flag, so it can tell the voltage controller, hey, I'm overheating, but it can't actually tell it, like, hey, I'm at 100 degrees or I'm at 90 degrees. It can't do that. That's reserved for smart power stages. This isn't smart enough to tell you what temperature it's at. Yeah, and that's the same as most of the other 5700s and 5700 XTs. Like, they don't use smart power stages for the minor rails. In fact, most of them don't even bother with smart power stages for VCore. They just go with the regular DR MOS components. So, yeah, it's kind of interesting how, you know, here you get some really nice VCore power stages, and then SOC is like, yeah, we're just a 45 amp NCP 3020 45. But this is still more, like, this is still plenty for the SOC rail, so I don't really see a problem with that. Moving on to the other rails, up here we have the GDDR6 power. Well, main GDDR6 power, because GDDR6 also has a VPP rail, and that sits at 1.8 volts and is probably, well, I'm not sure which side of the card it's generated on, but there's a voltage regulator on here that's either PEX rail, which is like PCI interface, and some of the some other internal stuff on the GPU. Like, I think it includes the display drive circuitry. There's another regulator on the back of the card, which is probably, like, one of the two is PC, like one of the two is PEX, and the other one is 1.8 volts. I'm just not sure which one's which. I'd have to have the card in hand to check. Anyway, so GDDR6 is powered by these two phases up here. Those are controlled by the NCP 81022, running in 2+1 phase mode. That +1 is for this rail down here, which that is the VDDCI rail. So that is the memory controller rail. So that powers the memory controller of the GPU. Now, VDDCI is on the same power stage as VCore, so that's another TDA21232. And why? It's because VDDCI is actually a relatively high current rail. On most AMD GPUs, like, the order of current draw basically goes VCore, VDDCI, then your memory, and I don't know what the SoC pulls, because I've never actually checked a card with an SoC yet. So, actually, does Vega have? No, I don't think. Well, no, Vega's an HBM card, so those get weird because HBM, like, pulls way less power than everything else. Well, the HBM memory controllers pull very little power, so those cards just don't compare to anything based on GDDR anything. But on GDDR cards from AMD, it's VCore, VDDCI, then the memory itself, and then, like, I don't know where the SoC factors into that, but considering that it's on a weaker power stage than the VDDCI rail, and it's got less phases than the GDDR6, it's probably behind both of those in terms of power consumption. Anyway, so VDDCI gets the slightly better power stage because, well, it's a power-hungry, it pulls, like, that rail pulls more power. The GDDR6 is just on more of the NCP 3020 45 power stages, and yeah, that's fine. Like, again, GDDR6 on other cards would be powered with 302155s or SIC 620s, or well, if you looked at the reference card, it would be FDMF 3170s, which are 70 amp smart power stages, but the reference card is freaking, like, ridiculous in that sense, where it's just like most cards are actually inferior to the reference card. Like, that's the situation with the PCB there. So it's just like, well, you can't really, like, you can't compare if you compared everything to the reference card, most cards are just worse, right? So it's just not real. And this is an ITX card, so this one at least has an excuse for not being able to fit the 70 amp smart power stages, because the thing is, they are actually, like, those are a 6x5mm package, whereas these are a 5x5mm package. And, well, I don't think, well, finding 2mm more for actually finding 1mm more space for every single power stage on this card, probably not an option, right? Like, they're already removing display outputs. So this thing is already about as cramped as it's going to get. Anyway, so yeah, the GDDR6 power is a downgrade compared to most cards, but it's really not a big deal. Anyway, let's go to the back of the card. So the thing I want to talk about next is the capacitor configuration. And here, like, the issue here is that this is definitely something that you'd need to take an oscilloscope to the card and check with an oscilloscope because, well, that's just the only way to tell if it's actually working. Okay? You can look and go like, oh yeah, this is a better type of capacitor. Doesn't inherently mean it actually leads to any meaningful performance, meaningful advantages. Or even, like, the thing is, even if the advantage was measurable, it wouldn't necessarily, be particularly big in terms of overclocking. But anyway, so the reference card uses a bunch of SMD aluminum polymer capacitors, which are great. They've got low ESR and low ESL, and they're very expensive. So all of the custom cards, basically all of the custom cards I've seen will replace all of those lovely SMD aluminum polymers with a bunch of through-hole aluminum polymers. Now, through-hole aluminum polymers can get just as low an ESR, that's not a problem, but the ESL on them is much, much higher, which means that for dealing with high-frequency switching noise, like the type of, like a GPU core can create, this style of capacitor should generally have an advantage. The obvious issue is that doesn't stop manufacturers from making like really, really bad ones, because the main reason why these exist is that they're low profile, right? Like, and that's the main reason Powercolor is using them here. But again, like there's a good chance like it might be a similar situation to what's going on with the power stages, where it's like the power stages on this are just better than what you get on a lot of the other cards because there's not enough space to have a big and efficient VRM. And so here with the capacitors, these probably perform better than what you'd get on a lot of the other cards. But don't take my word for it, because ultimately I don't even know who manufactures these ones. Like, I can tell these. And so these are for VDDCI, those are for the GDDR6, and this one, actually no, this is SoC over here. This is VDDCI, and this is the GD, and up here we have the GDDR6, right? But all of those are from APAC, which is a Taiwanese capacitor manufacturer, and they're really common on like cheaper motherboards, and well, I haven't bothered to look up the spec for these capacitors, but I don't really see a problem with these being used. Okay, like I've tested some motherboards with that actually use these for output filtering for vCore. It works great. They actually work just fine. Maybe they're not as high endurance as if you got them from like Panasonic or something, though funnily enough, I've yet to see a single SMD aluminum polymer rated for more than 2,000 hours. So I think that's just just due to how these are manufactured, you can't get them in really high endurance ratings. Anyway, for the vCore, however, I have no idea who makes those. Those, like, the markings are very obviously different from the APAC capacitors. They kind of look like they could be Kemet, but at the same time, like, no, because Kemets, like, instead, like, these have a plus here, and on a Kemet, I'd expect, like, a KO, and so I have absolutely no idea who makes these. That doesn't mean they're terrible, it just means they could be terrible. They could also be absolutely great and beat, all the other custom cards. And you might be like, okay, so best case scenario, how much better could these possibly be? I'd expect like 20 megahertz. I know I've just spent so long talking about capacitors, but the thing is, like, they wouldn't use the through-hole capacitors if they didn't have acceptable performance, okay? Like, so the difference you'd see between something like this at, like, like high-end aluminum polymers in the SMD packaging for the output filtering versus your through holes, I'd honestly on a GPU I'd expect like 20, maybe 50 megahertz core clock difference. And actually 50 megahertz would be like, whoa, like that would be really impressive. So yeah, anyway, I still think, like, ultimately I'm still sort of like, interested in this card just because we have all of these SMD capacitors, and these do tend to perform far better than your through-hole capacitors because of the lower ESL that they have, because your through-holes can still get the same ESR. So, yeah. That's the 5700 ITX from Powercolor. This thing actually looks very, very capable. Like, we've got great power, great 55 amp smart power stages for the V-Core VRM. Because honestly, even if I did these ratings at 1.8 volts, the VRM would be more efficient than, or actually, I think it ends up either more efficient or the same efficiency as what you'd get on most other 5700s anyway. So, like, these are just that overpower. Like, these are just that good. Like, at 1.8 volts, they're about as efficient as a bunch of other power stages at 1.2. Well, actually, efficiency is up, but the heat output is, like, the same. Right, like at 1.8 volts, the efficiency tends to be higher. It's just like the heat output is actually still absolutely ridiculously low. Anyway, and then for like the GDDR6 and the SoC, we get some downgrades, but who really cares about those rails? And then you just have a bunch of SMD capacitors, which is just like these could be really good. Like I'd expect these to actually perform really, really well. And so yeah, this could if you ignore the fact that this obviously comes with a tiny little heatsink. I'd be interested in like water cooling this card. Like I'd really be interested to see if like, hey, if you swap out the air cooler with a core only water block, could you push this further than the average full size 5700 XT? And you'd have to test like a pile of cards to prove that there's an actual advantage for this PCB over the other PCB designs. But still, like this looks really, really solid. And I guess the biggest concern would be just like the single 8-pin connector, but the thing is the single 8-pin connector right here can handle at least 300 watts all on its own. Like this can easily handle 300 watts all on its own. Because yeah, like that's not even like, that's actually like the low current variant of a, I don't think you can get a low current variant of this connector because that's solid, like those are solid metal pins. So yeah, like this connector is good for over 300 watts, no problem. The main issue though with the single power connector is that I'm not sure how the power is distributed throughout the card. And there's a good, and you know, being an ITX card, I think there's a lot of power is going to be jammed onto the PCIe slot. So if you start overclocking this thing, you wouldn't necessarily be pulling that much power. Like you'd be pulling less power from the 8-pin than you would maybe want to. Right, because this is going to be topping out at 150 watts stock, and this right here is limited to 75 watts stock. So it's like, are you actually, like, if you start overclocking it, how's the power distribution? Because if it's 1 to 2, right, for every 10 watts, like if you add 30 watts of power consumption with your overclock, 10 of those watts go to the PCIe slot. And 20 of them go to the 8-pin, which is like, well, if the PCIe slot was already at the power limit, that's not a great thing, right? So that's kind of, though there is still like, there's still some headroom built into the PCIe slot as well. It's just like you have far more headroom on the 8-pin power connector. But still, like this is like, you know, a rather interesting little PCB for a 5700, and yeah, that's it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, you can support me directly through Patreon. There's a link to it down in the description below. And if you'd like to pick up some like merch, like shirts, stickers, posters, that kind of thing, there's also the AHOC Teespring store. There's a link to that down in the description below as well. And yeah, that's it for the video. Thanks for watching, and goodbye.